Hi, so I recently bought this electric car, Hyundai K.O.N.S, and thought it'd be interesting to take a look at some of the electric car charging options, particularly the cheap ones from Aliexpress, just to get a feel for quality, safety, performance and so on at the cheaper end of the market. Firstly, I'll just quickly summarise the charging options for electric cars for those not familiar. Now, there's basically three options for charging electric vehicles. The first is this is a level 1 charger, affectionately known as a granny charger, because it's the sort of thing you use to charge when you're visiting your granny or somebody else that doesn't have a specific charge socket. These use the standard sort of wall socket. The charge current on these varies by country depending on what the current is available from their standard wall socket. Now in the UK we have these 13 amp plugs, but because of the fuse and the sort of heat issues, it's generally regarded as only safe to draw 10 amps continuously for extended period of time. So this one can charge at a maximum of 10 amps, and this car's got a 64 kilowatt hour battery. That means you're looking at about sort of 26 hours for a full charge. Other countries, for example in Europe, the K.H.O.N.S plug is quite common, which is rated to 16 amps, so you get higher charging rates in certain countries depending on what your standard electrical outlet can supply. And in fact, a lot of the better quality level 1 chargers actually have temperature sensors inside the plug, so that it can detect, for example, if you've got an old socket that's not in very good condition, that's a potential fire risk, the charger can actually detect that and shut down if things get too hot. This particular one can also be manually switched from 10 down to 8 or 6 amps. For example, if you're charging in a situation where you do have a plug that's getting too hot, or you're somewhere that's got not a particularly good supply, then you can reduce it, and obviously that does extend your charging time, but at least means you can actually charge. The second option is a level 2 charger. These are typically 32 amp, 7 kilowatts, and they're usually hardwired into a dedicated circuit on the house distribution board. There's quite a few of these available, and in the UK there's actually a grant available to subsidise the cost. And I think partly for that reason the cost of these are actually quite expensive. The complete cost including installation typically in the UK is of the order of sort of £750 to £1,000, but there's a £500 grant that reduces that to sort of £250 to £500, and there's various levels of sophistication. The basic charge functionality is exactly the same, but some of them have got like wireless connectivity and in theory connectivity to like smart meters, as well as doing things like scheduled charging. This one is an open EVSE. This actually comes in kit form with like a board and sort of self-assembly type thing. One of the reasons I got this was simply that buying the car was a fairly sort of spur of the moment impulsive decision. I happened to find one at a dealer, an ex-demonstrator at a dealer, so I just got this because I knew I could get it next day and install it. But there's loads and loads of different ones available, but so the core charging functionality is basically the same. Now these are typically hardwired in, but I've actually connected this to I've just installed a 32 amp outlet, so I can use different chargers, and potentially, for example, I could actually take this off the wall, and if for example I happen to know I was going somewhere that had a 32 amp socket, I could just take it with me. So the level 1 and level 2 chargers both charge AC. I mean, to call them a charger is a bit of a misnomer because they don't actually perform any serious charging functionality. The technical name is an EVSE, Electrical Vehicle Supply Equipment, or EVSE. And their basic function is just to decide when to switch the current on to supply the car, but also to tell the car how much current it's allowed to draw. And the third option is a DC charger, which you'll only find in things like petrol filling stations, and these connect effectively directly to the battery in the car to provide DC, and they can charge at anything up to sort of 150 kilowatts depending on what the car tells the charger it's expecting. So these will produce a rapid charge of typically around half an hour to an hour to charge up to about 80%. So that's the sort of thing you'd use like on a sort of mid-journey break, but obviously those are a lot more expensive and really outside the scope of anything you're likely to have at home. This is a charge connector. This is what's known as a Type 2 connector. Certainly in Europe, Type 1 and Type 2 are the sort of the common connectors out there, and I think Type 2 is becoming a bit more common. This has got a couple of different sections. We've got the top section, which is for AC charging, and we've got an earth pin at the centre, 2 pins for the main supply and 2 control pins, and you probably just about see one of those pins is recessed, so that's guaranteed to be the last one that connects, so that to make sure that all the other connections are made before the control signal can actually decide to switch anything on or off. And below this we have 2 pins. This is used for DC charging, and there's just a relay between these pins and the terminals of the battery, which is typically sort of 350 volts DC, and the charge currents could be anything up to 150 amps. And there's also 2 unpopulated pins here. This is because the standard also allows for 3-phase charging from AC up to about 22 kilowatts. So there are a few cars that actually have a 3-phase charger on board, but that's fairly unusual, particularly in Europe, because domestically 3-phase is very unusual in the UK. Obviously in places like Workplace, then it's more like you might have 3-phase, but I'm told that the newer model of the K.H.O.N.S might have a 3-phase charger as an option, but say it's relatively unusual at the moment. And inside the car, this is the actual charger. This is known as the OBC, or onboard charger. So this takes the mains from the connector and converts that to DC to charge the battery at something of the order of sort of 20 to 30 amps DC, depending on the battery voltage. This has liquid cooling on it. It's a 7 kilowatt charger. You can see the input actually ranges from 70 to 285 volts, 35 amps max. Obviously it wouldn't do 7 kilowatts on a 110 supply. And you can see the outputs 225 to 420 volts DC, up to 21 amps maximum, and total output power 7.2 kilowatts. So I thought it'd be interesting just to see what's available on Aliexpress in terms of the cheapest 32 amp chargers I could find. And interestingly, although most of the chargers in the UK seem to be sort of permanently installed wall mount, pretty much everything on Aliexpress is sort of plug-in. This is supplied with a standard 32 amp plug, these go by various names, Commando, C-Form type plugs. These are very common in the sort of entertainment industry and in industrial uses where you want higher currents. And in fact I couldn't find any sort of hardwireable dedicated wall mount ones at all, but of course there's no reason why you couldn't use one of these in this situation. And I think for flexibility it probably makes sense to install a 32 amp socket rather than necessarily you having even if you've got a hardwired charger, because it does give you the option. For example, if your charger has a fault, it means you can just plug another charger in easily. I've just got a fairly standard socket now. Strictly speaking, for a domestic situation, what you should really install is an interlocked socket, because one issue on these sockets is that unlike standard UK 13 amp outlets, there's no shuttering on the connector. So in principle, inquisitive figures could sort of jab something in there and you'd have mains on there. But you can buy fairly cheaply an interlocked socket, and that's designed, it's basically a socket and a switch in one box, which is designed so that you can't turn the switch on unless there's a plug inserted, and you can't remove the plug while it's switched on. So for a sort of normal domestic installation, especially if you've maybe got kids around, I definitely recommend that you use an interlocked socket. Now the actual functionality of these things is fairly simple. They've basically got 3 jobs. Firstly, they need to tell the car how much current its onboard charger is allowed to draw, and this is done using a 1 kHz square wave signal on that on the pilot pin, which is the recess pin, and the duty cycle of that square wave tells the car what its maximum current draw can be, and that ranges between 6 and 32 amps. Secondly, it then detects the car putting a load on that signal and uses that to turn on the main supply. These have all got relays or contactors to connect the main supply to the car. And thirdly, they've got some safety functions, in particular earth leakage detection, depending on what countries you might recognise as a ground fault current detection, residual current detection. It's all the same thing. It's basically detecting any leak to earth, for example from a damaged cable, or if someone drops the end of the cable in water, or if there's some fault on the car that causes some leakage to earth, it trips out. So those are really the basic functions. Another sort of desirable feature, which has actually become part of the UK wiring regulations for hardwired fixed charge points, is that as well as the normal approximately 30 milliamps residual current trip, it also should trip on a DC leakage situation. Now, in a car you've got massive 300 volt DC battery, so it's conceivable that some fault on the car could result in DC earth leakage. And there are actually 2 separate issues here. Firstly is actually detecting that situation. Now most standard residual current devices use an AC current transformer and won't detect DC leakage. But secondly, these things would typically be plugged into a circuit that has some residual current protection upstream. And if there's any DC leakage, this can cause a problem, because that DC leakage can saturate the current transformer in the upstream protection device and actually prevent it tripping on genuine AC current faults. So if this is sharing a circuit with other load or even just wiring, a DC leakage fault can actually stop that tripping. The UK wiring regulations only apply to fixed wiring, so if you're installing a fixed wall mount charger like this, then the charger should have DC protection. Things probably get a little bit more vague if you just install a generic 32-pin outlet. Then there could be arguments made that this is a general purpose socket and not an EV charging socket, so those regulations don't apply, but that's really an administrative argument to have rather than a technical one. Obviously, the chances of having a DC fault are pretty low. So, and the granny charger, certainly I know the Hyundai granny charger doesn't detect DC faults, because I've actually done some tests to verify that. I suspect these two probably don't either, but we'll do some tests to actually measure the actual residual current performance to see whether they can actually detect that or not. But lack of that, I wouldn't say is a huge issue, because it's a pretty improbable fault situation. So you obviously have to balance the likelihood of that happening versus potential consequences. But obviously the primary thing is AC fault detection, and in this situation, the most common likely scenario is a cable that's maybe got damaged by being run over or by repeated flexing, or water ingress into the plug. An AC RCD will generally detect that. So I'm just going to go through the functionality of these first, and then we'll take them apart and have a more detailed look and do some tests. These were both almost exactly the same price. I'll put all the details of where I got them from and the price and so on in the video description below. And so we've got two. One is labelled Zencar and the other is labelled Khons, K.H.O.N.S. One of them also has the name Duoceder on the plug. As with all these Chinese things, it can be a little bit hard to figure out who the actual manufacturer is. There's quite a few charger units which are branded Duoceder. Now, whether they make them or not, who actually makes what is pretty much anyone's guess. But so these are sort of two very common ones. So I'll start with the Khons unit. It's sort of plastic case. Feels reasonably rugged. It's not like super quality plastic. I doubt if it would tolerate being run over though. It's got a little flip up hook so you can actually hang it on the wall. Both of these, they're rated IP54 for moisture ingress. Obviously I wouldn't generally want to leave these outdoors, and particularly you wouldn't want them anywhere they got direct sunlight, because that would degrade the plastic over time. One thing that would be nice if you're using these in a sort of more portable scenario is if you could actually get some sort of rubber boot, which is common on sort of multimeters, to give them a bit more robustness, but I've not seen any that actually give you that option. So on the front there's 3 LEDs and a nice little OLED display. The OLED might look a bit flickery on camera, but that's purely a camera effect. It looks perfectly fine when you're close up. The viewing angle on this is a bit limited because where the display is in the unit, as you tilt it up, it starts getting cut off by the case, so you need to view this fairly straight on if you want to look at all the figures. And this has got pretty much all the information you want. You've got total kilowatt hours charged, charge time, supply voltage, current, kilowatts, internal temperature, and the current charge rate. Now, neither of these have actually got any external buttons. This is presumably just for robustness, but they use different methods to set the charge current. In this one, it's actually got an internal accelerometer, so what you do is you actually shake it to set the current. So it goes through 8 amps, 16, 20, and 32 amps. These settings are non-volatile, so if you unplug it and then plug it in later, it keeps the same setting until you've explicitly changed it, and it only looks for that apparently within the first minute or so of being powered up. One thing I don't like about this is it doesn't have a 10 amp option. So for example, if you're using this as a general purpose or charger, you might want to take a lead to plug that into a 13 amp socket. But, the best you can get is 8. There's no 10 amp option, which I'd have liked to have seen. So if we plug it into the car, see connected. Couple of clicks from the car, and you can now hear the relay clicking in to turn the power on to the car. So we're now charging. We're showing the current 29.7 amps, 7 kilowatts, current supply voltage 235 volts, charge time. Both of these use a red light to show charging and a yellow light for an error, which I think is really the wrong way around, because red is generally associated with like faults and errors. So I think red should really be a fault and yellow for the charging. One thing I don't like about on both of these chargers is there's no way to manually stop the charge. Now you can't just pull the plug from the car because there's a mechanical interlock on there that locks it in, because you don't really want to unplug this when it's passing 32 amps, because you'd tend to get some arcing, which at the very least would damage the connector contacts. If you've got a switched outlet, you could just turn it off at the outlet, but that's not ideal, because again you get wear and tear on that switch if you turn it off when it's passing 32 amps. Different cars probably handle this in different ways, but in this one, if you just hit the unlock button on the remote, it will stop charging and unlock the charge connector, so you can then just pull that out. So now let's take a look at the Zencar unit. This is slightly bigger. It feels a bit more robust. It's got this sort of fairly sort of solid wall all the way around on both sides. It just feels a bit more solid. The Aliexpress listing sort of claims that you can run over this in the car. I'm not sure how well it survive that, but it does actually feel sort of pretty rugged. You've got a slot and a hole there for mounting there, and another couple of mounting holes on the bottom, so it'd be quite easy to wall mount there. Now this uses a different way of selecting options, and there's actually two different ways of doing it. There's a touch contact here, and you can see the LED lights up when you touch it, and a double touch cycles through the various options. So we've got the current options. We have 10, 16, 20, 24 and 32 amps. And obviously having a 10 amp option, that's potentially useful if you want to use it in conjunction with 13 amp main sockets. The other option is you get two of these RFID tags with it. And again, these just flick through the options in the same way. Now, RFID does seem a little bit overkill for something like this. I wonder if perhaps the board, it can also be used in applications where they want to use RFID for access control. There is also an option for delayed charging, which can only be operated by the RFID tag. So we've got a similar display of sort of time, voltage, charge current, etc. Again, we've got a temperature indication. It's also got a little earth indication, which I'm guessing is an earth disconnection detection, which again we'll test that to see if how that works. So if we plug this in, for some reason it shows a picture of an airplane when it's connected. I don't quite understand what the relevance of that is. And then it starts charging. So again, we've got the running display of kilowatt hours, time, etc. Now, one thing you can also do is once it's connected, you can use this RFID card to delay the start of charge. So if you put it on there, it shows 2 hours, 4 hours, 6 hours, and then it counts down. So there might be situations where you want to delay the start of charging, for example if you've got a cheaper electricity rate, or perhaps if you've got other really heavy loads like an electric shower and you don't want to have the car charging and that shower pulling power at the same time. But that's the only additional function on this versus the K.H.O.N.S unit. So that's the basic functionality of both units. They both work, they both charge the car. They both got slight limitations in that you can't stop the charge from the unit, but other than that they're pretty much the same. So now let's actually take a look inside and actually make some measurements and see how they actually perform, and see what the build quality is like. If you're not interested in these technical details, then just skip to the end of the video and I'll do a summing up. Right, so let's take a look inside, starting from the Khons unit. On both these, the screws are behind the label, so you need to peel the label up. And in both of them, they do actually use machine screws into threaded inserts, not self-tappers, so that's quite nice from the robustness point of view. The Khons unit also has little rubber pads on top of the screws as well. It's got a sealing gasket there, some sort of ribbing to reinforce the case. Whether that would, I'm not sure how much pressure that would give at the centre, because there's only 4 screws on this one. The Zencar's got 6. But the case looks fairly well made. It's standard ABS, nothing particularly fancy, but say it seems to be reasonably well made. So we can see we've got a display board here, and then all the electronics are on this baseboard. So first look, internal build looks fairly reasonable. The relays are made by Honstar. These are 50 amp rated relays. They're latching relays. I suspect the reason they use that is just to minimise internal heating. Obviously a 50 amp relay is going to have fairly chunky mechanical parts, so a non-latching relay will probably need quite a lot of current to hold that in, which would just contribute to internal heating because the power dissipates in the coil. So in here we've got like a little modular switch mode power supply, 2 relays, we've got the current measurement transformer there, and then we've got the leakage sensing transformer here. So everything's on one PCB. There is some conformal coating on the board to give a certain degree of moisture resistance. There's a large capacitor here that looks like it might be a slight afterthought. I think that may be so that if it gets unplugged from the mains, it's got enough power to delatch these latching relays. Now really annoyingly, it looks like they've crimped these connectors on after they've passed the wire through the current transformer, so you can't actually get this board out without chopping these connectors and re-crimping. So looking at this PCB, build quality looks generally okay. It does have conformal coating, but unfortunately they've done the typical stupid Chinese thing of scrubbing the numbers off the chips, and they've put some blobs over here, so it's a bit hard to tell what's actually going on. Quite surprised to see two fairly large chips here. This I'm sure is the main microcontroller. You've got a resonator there, the accelerometer is connected to it, and also goes to the display. But I'm a bit puzzled as to what this chip is here. Now it might be something to do with doing the AC measurements. It's got a different pin count to the micro, so it's not like they've used sort of two separate micros or anything. There's also this resistor that's been bodged across the resonator. So that may be to do with startup issues. Sometimes if you've got startup problems on ceramic resonators and crystals, adding a little bit of feedback, this 10 meg resistor, that can just help it start more reliably. This, which is obviously a programming header, only seems to be connected to this device here. So we've got the two latching relays here. The terminals are obviously very close because you don't want to have 32 amps running too far across the PCB. Just feeling, this doesn't feel like it's a heavy copper PCB, it feels like a fairly normal copper thickness. Yeah, the current carrying tracks are duplicated on both sides, and there's fairly extensive through vias, and we do have some isolation cutouts here, so I think the all the clearance is probably okay. It looks sort of reasonably well designed. And so we've got this huge capacitor, 6800 microfarad capacitor bodged across here. Now the only reason I can think of is to give this enough power to delatch the relays if the power goes off, but that doesn't actually appear to work. If you switch it off, the relays don't unlatch, and then next time you turn the power on, they do unlatch after about a quarter of a second. So not ideal, but it's hard to imagine a scenario where that would be an active problem. One thing I was quite curious about both of these is how they did the mains voltage measurement, because the control circuitry is referenced to the mains earth, which is because that's the pilot signal to the vehicle is referenced to earth. So I was a bit curious how they actually did that mains voltage measurement whilst keeping it isolated. And what they both use these little transformers specifically designed for isolated measurement of mains voltages. Seems to have a reasonable degree of filtering. There's a connector here which is for a plug temperature sensor, and obviously that's not used on this device. It looks like it does actually, you have the name Khons here on the PCB, and that's 2019, so it's a fairly recent device. So let's just check the heating. This has been charging at 32 amps for about half an hour. The onboard display is saying 33 degrees C, case is 25, input lead 29, output 27, and internally the relays and the connections 35 degrees, which is fine. Power supply modules about 42. The hottest part is actually the resistor that's in series with the voltage measurement transformer, 4950, so that's about the hottest thing. The ambient's about 17 or 18, so I don't think there's anything getting worryingly hot there. Okay, so let's take a look inside the Zencar unit. Now this has got 6 screws, again like the Khons there, machine screws with proper threaded inserts in the case, which is nice, but you still have to take the label off to get to them. So internally we can see they are a little bit different. This one, we've got most of the control electronics are on this front PCB with just the power stuff on the bottom. Again, we've got one of these blue transformers for the mains voltage measurements. The overall layout is a bit less cramped, but also it's a lot easier to get apart, because here they've put the earth leakage current transformer over the cables. Instead of being attached to the PCB, it's actually a separate device that plugs in, so although you may or may not be able to get those tags back through the transformer, it doesn't matter because the whole thing can come away, so you can get the board out. And this single one for the current measure transformer is small enough that will actually pass through the transformer, so you can actually get all these boards out really easily, whereas it's an absolute pain on the other one. You actually had to chop the crimps off and recrimp them, and that was because the space was so cramped, that was actually really tricky. So this one on first look is certainly a lot easier to get apart. Now this uses the same 50 amp Honstar latching relays. The difference is this uses a version that's actually got that's got a manual operation and indication tab on it. So if you turn them on, you can actually see the tabs flip. And the other thing is, if we now turn the mains off with it on, it does pull the relays back out, so there is enough stored energy here and it can detect the power down fast enough to drop those relays out, which the Khons unit didn't do. So from that point of view, this is definitely an improvement. And if the relays just happen to somehow be on when the mains comes on, turn it on, it does click them out fairly quickly. On the back of here there's a marked connector, but this is for a plug temperature sensor, and this will actually display on the OLED display if we connect something to it. And if we connect, I'll just connect to the 10k resistance across that, and we can see now it's alternating between plug temperature and internal temperature. And if I reduce the resistance, you'll see the plug temperature value rising, and then at some point it's decided it's got too hot. We've now got a fault indication, and now it won't turn on. And the case does have a soft gasket here, and we've got 6 screws retaining it, so I think I'd be a little bit more confident in the moisture proofing of this than the other unit. So this top PCB's got sort of most of the electronics on it. It all looks pretty straightforward. There's STM32F103 processor underneath the display. There's an NXP RC552 RFID reader for reading that RFID tag, so it seems a little bit over the top for just that simple setting function, but so I'm guessing that it may well be that this board is also used on products that use RFID for access control and maybe other features. Not really much else. There's an MV324 op amp, power supply stuff. There is an unpopulated chip here. There's not that many pins. My best guess for that is it's an option for an accelerometer for the shake functionality you saw in the other unit. A couple of unpopulated connectors. I've had a prod around those. I can't really see anything obvious, but other than that, sort of, you know, fairly straightforward. Again, this has been conformally coated, so to give it a bit more moisture resistance. And we've got just a touch, obviously that's a touch sensor chip of some sort, and there's just a spring. I don't think there's actually any metal on the front panel. There might be some metal between the this and the plastic, just to increase the size of the sensing electrode, and also because it's an identifiable processor, 32F103, then you could potentially reflash this with your own firmware if you wanted to do something a bit more exotic with it. So this board comes out much easier than the other unit. The neutral wire come through that current transformer without taking the tag off, so that's much nicer. And so this board is pretty much just power components. The RCD current transformer is there off the PCB, just plugs in. One thing that's quite notable on this is there's much shorter tracks carrying the main current. Both the live and neutral in and out connectors are right next to the relay contact, so there's there's a very, very small amount of track, so that just reduces the potential for PCB heating. Again, I don't think this is a 2-ounce copper PCB, I think this is fairly standard, but again we've got the tracks are on both sides of the PCB. Unlike the other one that had a power supply module, this has got a discrete switch mode power supply for its low voltage, but we've got decent amount of proper filtering, sort of creepage distances on here. Again, both boards have got conformal coating on, so that gives a bit of moisture resistance. This is a power supply control circuitry here. It's got a nice sort of cable connector rather than the FFC cable, and the other one was a little bit fiddly to get on and off. This one's a bit nicer. So overall, no sort of major surprises there. I do prefer the construction of the Khons unit. It's a lot less cramped, although the unit's not actually that much bigger. They just seem to have done a slightly sort of more thoughtful layout. Notice it's got these reinforcing ribs on the side. One detail that is slightly different, both of them use these 2 relays, so you've got some redundancy from the point of view of, for example, a welded contact, not affecting the other relay. The K.H.O.N.S unit actually has separate driver transistors for each relay coil, and in fact when you turn it on, you can hear a very slight delay between the 2 relays clicking in. This one basically has the coils connected in parallel. Don't really think that the redundancy of that makes a lot of sense. You're in terms of reliability and sort of failure mode, you're so far down the list of potential issues that I don't think it's relevant. And the fact that this seems to deal better with the latching relays is a much bigger thing than just having that additional redundancy on the relay drives. Well, they'll just notice there's actually like a little handwritten label with the current settings, 10, 16, 20, 24, 32, some sort of number. I mean, I imagine like a lot of these Chinese products, there's probably a few different firmware variants. If you look on Aliexpress, there's quite a few devices that look similar with different names on them. Let's look at some of the actual functionality. Now, just for a reference, I'm using the Hyundai charger, which is made by Ura, who are, I think, a fairly major charger manufacturer. So basically all the control happens on the pilot contact to the connector relative to ground, and the charger outputs a square wave, the duty cycle of which indicates the maximum output current. When the car connects, initially it connects a resistance through a diode to indicate the status. So the first status is connected, so if we just connect that, we see the car's lit up, and then this goes down to about 800 ohms to indicate charging. And that's now in charge mode, and the relay's clicked on to enable the main supply into the vehicle. Now the reason there's a diode here is to provide some protection against accidentally operating. For example, if you've got a damaged cable or water in the connector, then it's quite possible you'd see some resistance to ground, which could cause this to turn on when you don't want it to. The square wave signal from the charger is bipolar. This spec I think says it goes from plus 12 to minus 12, so the diode introduces some asymmetry that you wouldn't normally see. Any normal fault condition wouldn't produce that asymmetry. It needs that diode to produce that. So let's see what happens with the Hyundai charger if we don't have the diode. If I just bypass the diode and we go to the initial connect stage, and see we're now getting a red error light there, and we have to power cycle it to reset. And we'll just do the connected, and again we get an error, so it's not turning the power on unless it sees the diode, and that's the behaviour we expect to happen. So we'll try the same thing with the K.H.O.N.S charger, again with the diode. So the initial connection mode this turn changes to connected, and we get the green LED flashing, and then we go to charging state. This changes to charging, we get the red LED. So that basic function works. Let's see what happens without the diode. Okay, so without the diode it's still recognising the connected state, not giving any error, which it should be giving an error. And we're now in the connected state with no diode and it's still turned on, so that is not behaving correctly in terms of potentially outputting voltage in say a fault condition where there's leakage on the cable. Let's see what happens if we reduce the resistance to emulate, for example, a shorted cable. Okay, so if we reduce the resistance too low, then it does actually give us a fault indication. So a shorted cable will make it not turn on, but the fact that it's not caring whether that diode's in circuit or not means that it isn't compliant with the charging spec that it's claiming to be compliant with, and that's one safety feature that it doesn't implement correctly. Let's do the same test on the Zencar. Go to the initial connection, we get the connection and the picture of an aeroplane, and in the charging mode it turns on as it should. If the resistance goes too low, then we get the error indication, it cuts out, which is exactly how it should behave. Let's try it without the diode. So direct connection. Now connecting mode, it is registering that's connected without the diode, and it is charging, so again this one is also not checking for the presence of that diode. Checking just for a simple cable short. Yeah, it has to go down to about 100 ohms before it recognises that as being a fault when it's just a cable short. So neither of those are actually testing correctly for the presence of this diode. Now what I find really strange is why they haven't implemented this. Now in terms of component cost, generating the bipolar supply is probably the biggest cost, and both of them do that correctly. This is the waveform from the Zencar unit, which is generating the plus minus 12 signal. It's limited there because I've connected the diode. This is the diode in connected mode. So having generated that bipolar waveform, basically all it has to do is detect the difference between this, which is the waveform with the diode there, and this, which is the waveform without it. So although it's negative, that's easy enough to level shift to produce something that a microcontroller could easily detect. So I just can't imagine why they wouldn't have implemented such a basic thing. I mean, I don't know if there's some reason, with maybe certain cars being temperamental or not implementing it. I really don't know. If anyone does know, then please let me know. But it just seems really peculiar that two devices, which they look like completely different designs, it doesn't look like one's a copy of the other, have both omitted such a basic and easy to implement feature. It just doesn't seem to make any sense to me. Okay, let's look at the earth leakage performance. The setup I've got here, I've just got some resistors connected to the input neutral via a current meter, and I'm then going to connect that to the output live, so this will produce an imbalance. I'm not doing it to earth just to avoid tripping my incoming earth leakage breaker. So what I'm going to do is I'm going to reduce the input voltage, and then as I increase the voltage that's also going to increase the leakage current. So we'll see at what point it actually trips. So I've set the pilot signal to turn the output on. So this is the Khons unit, 17 milliamps, 20, so that's tripping out about 20 milliamps, that's fine. The other thing I like about this unit is that after it's tripped it doesn't self-reset, so if you've got some transient issue, it won't clear itself even after you've unplugged the car. You've got to actually power cycle the unit, so that's good. And now the same test with the Zencar unit. trips out 23 milliamps, which is fine, shows a fault on the display, but this one does self-clear, so it trips, but as soon as you disconnect the car, and it will latch so that, you know, if you come back to the car it will be tripped and not charging, but the car might sort of detect the fact the power's gone, and you know, you could get a some sort of cycling. So this is slightly less good in that it doesn't latch until you power cycle to reset that fault condition. Okay, let's see if these have got any sensitivity to DC faults. What I've done is I've just got a DC bench supply and a series resistor that I'm going to connect across between the input neutral and output neutral to produce some DC current through its current transformer. Increasing 50 milliamps, and no trip up to, you know, over 100 milliamps and no tripping. And a sudden DC fault will generally produce a trip because of the AC command. If I sort of suddenly disconnect this, then it does trip, but a gradually increasing DC fault doesn't cause it to trip, which is fairly expected because it looks like it's using a normal AC current transformer. And let's check the Khons unit, which I expect to be the same. Yeah, no trip up to 100 milliamps, but probably a trip if I suddenly disconnect it. Yeah. So that's pretty much as expected. Now, I don't know whether the standards for these sort of portable units actually specify DC performance at all. So the only place I know for certain it's include the latest edition of the UK wiring regulations where they specify a 6 milliamp DC current trip. Now the fact that this shows this little earth symbol makes me think that maybe it's capable of detecting a missing earth. And indeed, if I disconnect the input earth, we see a little exclamation mark, but it doesn't stop it working. It'll go into connected mode and switch on, despite the fact the earth's off, so at least it does give you a warning. The Khons unit and also the Hyundai unit don't detect earth missing. So that's potentially, if you're plugging into some random socket you don't know, at least it's good to have some sort of warning that, you know, in case of fault condition your whole car might be live. But you've still got the earth leakage protection there, so it's not a huge deal that it doesn't actually prevent you using it if it thinks the earth is dodgy. So let's just check for heating. This has been charging at 32 amps for about half an hour. The onboard display is saying 33 degrees C, case is 25, input lead 29. Output 27, and internally the relays and the connections 35 degrees, which is fine. Power supply modules about 42. The hottest part is actually the resistor that's in series with the voltage measurement transformer, and that's about 4950, so that's about the hottest thing. The ambient's about 17 or 18, so you know, I don't think there's anything getting worryingly hot there. So temperatures on this one's been running for about half an hour. Again, we've got about 29 degrees on the output cable, about the same 31 on the input cable, and inside, and we've got nothing over 40 degrees there, 41 at the bottom of that relay. So yeah, all perfectly fine temperature wise. Reading 36 on the internal display. The quality of the cables on both these looks fine. In fact, the actual cable manufacturer is the same for both of them, and I think the so is the plug. The 32 amp plugs, again, those look perfectly good quality. Both of them have used ferrules on the screw terminals. They've both got double screw terminals, so that's all perfectly fine. No complaints at all about that. So to sum up then, both of these will charge your car just fine. They're not going to burn your house down. There are some minor issues with the diode check. Now, in terms of safety, I think, you know, it's a pretty small window of potential problems there. Basically, in order for that to be an issue, you'd have to have some sort of fault on the cable or the plug, which put a low enough resistance on the pilot signal to get it to turn on, but not so low that it produces a fault indication. Now, that those turn out to be 800 to 1200 ohms on the K.H.O.N.S unit and 800 to 2000 ohms on the Zencar. That's certainly way below anything you're going to see with like water ingress. Probably only going to be literally a cable that's been quite badly shredded, and even then you've still got the earth leakage. So basically you'd have to have both the combination of that fault and not enough earth leakage to trip the earth leakage breaker to cause a problem. So personally I would have no worries at all using these, you know, on a day-to-day basis as my everyday charger. In terms of choosing between them, they're both about the same price, about £260 delivered to the UK. I was fortunate on both of these I didn't get charged duty. You might get charged VAT and import duty, so you have to factor that in and just treat it as a bonus if you don't. Between the two, basically I don't really see any reason to buy the K.H.O.N.S unit. The Zencar one has got the additional functionality of the timer, it's got a more rugged case, it's better built inside. So for example, if you ever had to replace the charging cable, it will be a real nightmare to do on the K.H.O.N.S unit because the thing is just so packed tight, it's really difficult to take it apart and put back together again. It'll be much easier to do on the Zencar, and the Zencar in general is, you know, it's a lot more potentially repairable. You've got you don't have this sort of shake thing, a fairly simple sort of button control and these tags, which I don't think are really that useful in this application. I can't think why you'd ever actually want to use those. So, you know, although the basic charge functionality is about the same, you know, if this one was significantly cheaper there might be a reason to go for it, but I think at the same price I don't think there's really any significant advantage. There's a minor thing, like for example some of the fault conditions will actually lock out until you power cycle it, but I think again we're getting really down into the weeds of differences. So yeah, if you're looking to buy one of these, I'll definitely go to the Zencar one at the same price. There's no real reason to go for the K.H.O.N.S one, I think, but yeah, I think these are, you know, perfectly reasonable chargers. The lack of the DC protection, that seems to be common to pretty much all portable chargers. As far as I'm aware, the DC trip requirement is only something which has been very recently introduced into the UK wiring regulations. So, you know, I don't quite know the reasons for that, whether it's a theoretical risk, whether there have actually been some problems. But again, you know, you're going to have to see multiple faults occurring, all of which are fairly unlikely for that to be an issue. So, yeah, I really wouldn't have any concerns at all about using these. The only thing I would say is that if you're using these domestically, that I would use an interlock socket rather than a standard 32 socket, just to prevent any risk of anyone sort of poking curious fingers into the plug. But apart from that, you know, I think these are perfectly fine, nice cheap solution, maybe useful as a backup solution if you've already got an existing charger, and very good at, say, if you've got a portable situation, if you frequently work at places where they've got 32 amp outlets, which are quite common in industry and also in like TV film production, that sort of thing. To be able to charge at 7 kilowatts from a portable thing, I think it's actually quite a convenient option. And I've put details about where I bought these down in the video description, as well as delivery times and that sort of detail.